going to talk about products and services for AE, architecture and engineering. Do we have the moderator and the panelists all online?
We're
All
all
online.
here.
Okay. All right. Great. All right. Well, uh, Maria, it's in your hands. So please go ahead.
Wonderful. Thank you. Hopefully, everyone is back from lunch and grabbed some caffeine on the way. We don't want any food comas this afternoon. I'm really pleased to be here and be leading this session for C. This is the complement that Dan mentioned yesterday. It's a session to the engineering insurance-focused discussion, looking now at the transition of science between producers and the A&E community. When I first picked up this session, I want to quibble a little bit with the session description that suggests that there is a beginning, middle, and end to this transition. Of course, it's a cycle, right? We know this, and it's characterized hopefully by sustained relationships and ongoing communication and collaboration that supports the production of information. And it ensures that, as my former office director at NOAA, Margaret Davidson, used to say, we're producing products that are not just useful, but are actually used, right? That really is the aim of this task force, as well as the things that we're talking about today. Oh, I should mention, I am with Atkins Realis, which is a professional services and project management company. We've got about 40,000 people scattered across 6 continents and about 4,000 of us here in the US. And I'm a bit of a boomerang. I started my career with the predecessor company, PBS&J, but then spent a wonderful 15 years in the federal government, both on the Hill and with NOAA, where I got to know many of the people that are here in the room and speaking over these 2 days, working in partnership on the policy and the production side of things. And now I have moved back over to the dark side. No, I'm kidding. As we say, that last bit of the last mile, where we are working with project owners, both in the public and private sector, to try to derive the maximum resilience and sustainability value out of the investments. And our company works across buildings, transport, water infrastructure, energy, including nuclear power. And so Eric is sort of my kindred spirit here on the panel as some of the representatives from this community. And others will talk about it. You know, we're not alone in that we use and rely upon a lot of NOAA data in both planning activities, design, even operations of facilities and utilities. And our R&D investments in our firms often are building upon and ingesting NOAA and other public data to underpin both modeling and apps and other things. And we're affected, right, when there are changes in federal priorities. And I think a perfect example of it, I've been trying to listen for it, I haven't heard it come up yet, is obviously what's happening with Atlas 15, specifically Volume 2, and it's defunding, right? And those forward-looking projections, precipitation, are vitally important to ensuring that our investments last as long as intended. That phrasing is, so shout out to my folks in the room that have worked on the Federal Flood Risk Management Standard. That was sort of the central reasoning behind saying if we're going to build things with taxpayer dollars in particular, we need to ensure they last as long as intended, but we need the data and information to underpin that. So there are also things that are affected by not just federal policy, but state and local. And I think it will come up in some of our conversation today that sometimes beyond building codes, you have policies and guidance that are adopted at a state or state agency level that can incent resilience building, and others that may constrain it, like what sea level rise scenario are you allowed to use or not. But I don't want to get too far, and from those examples and robust conversation, I'm really excited to have a fantastic panel before us. Just to introduce them very quickly, Dr. Tom Delworth, who is a senior scientist at NOAA's Geophysical Fluid Dynamics Laboratory, Dr. Kelly Mahoney, a research meteorologist with NOAA's Physical Sciences Lab, Dr. Abby Leal, professor of civil, environmental, and architectural engineering at University of Colorado, Boulder, and finally, Eric Zucker, a structural engineer with HNTB. So what we're going to do with our time is we're going to turn, and I know you all are driving the slides there in Ruston, but we're going to have each speaker will give 4 to 5 minutes of remarks talking about where they work in this virtuous cycle of translating science into engineering practice, and then we'll pivot to some questions. I would encourage folks, I think people have been using the Q&A box. I will have a couple of questions that I will pose to the panel, and then we certainly want to open it up to questions and Q&A. And I don't know if it's Dan or Bilal or Erica, someone in the room, to kind of help when we want to open the door to questions in the room. All right, all good? I can't see anything, so other than the PowerPoint, so I'm going to assume, unless someone says otherwise, we're doing well. All right, Tom, I think that means that's your cue to take it away.
Great, thanks. So you can hear me okay?
Yes. Perfect.
Okay, thanks so much. So my name is Tom Delworth. I think I'm either upstream, downstream, or sidestream of most of the stuff going on here. We'll find out. I'm at the place called the Geophysical Fluid Dynamics Laboratory. We're a part of NOAA. We're a part of the Oceanic and Atmospheric Research. And we are a laboratory that really focuses on building numerical models of the coupled ocean, atmosphere, Earth system, primarily for understanding and translating that understanding to prediction. So that's our mission, has been for quite a few years. So we use models, we develop models for specific questions. So first, just very quickly, what is a model? A model is a numerical encapsulation of the sort of the physics dynamics of the Earth system. You can translate the fluid dynamics, the physics, the radiation into equations. We discretize those, and we break up the Earth's ocean and atmosphere into a series of boxes and numerically solve those equations on each of these boxes. The number and size of those boxes is absolutely crucial. It's limited by the computational power we have available. The smaller the box, generally, the better situation we're in. So we develop a wide range of models that span timescales from 1 hour ahead to 1 century ahead. We'll focus a little bit on the longer time scale here. We do things, for example, like seasonal to decadal prediction of climate and extremes. We actually participate in, have developed models for this and participate in real-time seasonal and decadal prediction of climate and extremes. And one of the key aspects is we're doing that prediction in the context of changing rate of forcing. So it makes for a very complex system. So we try and optimize those models for understanding and predictive skill. We also do longer-term multi-decadal projections using large ensembles of models to better quantify the potential uncertainty in the climate system, the variability. And a key mission there is really quantifying the likelihood of changing extremes, whether it's precipitation, storms, et cetera. But the real issue here is that the question we're posing really determines the appropriate model. There are many different spatial and temporal scales that are involved in different applications, and that really dictates the types of models that are most fruitful for applying to problems. So I list here some relevant NOAA models that may be of use and utility. One is called SPEAR. This is our model we use for predictions. I list the resolutions here, a 25-kilometer atmosphere and either an 8 to 25-kilometer ocean. Those are really key. Most of the global models used for things like IPCC use much coarser resolution, say 100-kilometer atmosphere. So those grid boxes that we tile the planet with are of size about 100 kilometers on a side. Our models are finer resolution. That's really critical for simulated extremes. We've shown that very clearly. So we're really focused on extremes. ESM 4.5 is another model. Again, models differ in their constitution depending on their purpose. ESM 4.5 is coarser, but it includes things like biogeochemical processes. And a third model called SHIELD is a much, much finer resolution, 3-kilometer model, and it's used for short simulations and what we call time slice experiments. We can get into that later. So there are a variety of different models for different purposes, but the key is that what question are you asking? So if you go to the next slide, please, I'm just going to show one result example from our SPEAR simulation. And these are the kinds of questions we can ask with these models going to the future. So we're asking the question, how do extreme precipitation events, how will they change in the future over, in this case, the Southeast United States? So we run these large ensembles of simulations. We make estimates of future changes of atmospheric composition, and we simulate these. And we run many, many cases so we can get a good statistical description of what's going to happen, distribution. So here, the y-axis is the number of years, the number of 1 in 100 year precipitation events simulated each year over this region. So a black dot shows how many sort of once in 100 year events we'll see over the entire southeastern US within this modeling framework. So, and the x-axis is time out to the year 2100. We see, first of all, these black dots going up in time. But secondly, if we look at the box that says 1990s and the box that says 2020s, those are two different epochs. And the changes there are merely a manifestation of changing atmospheric composition. But you notice there's no overlap at all in those black dots. So it shows that in the 2020s, at least from our modeling perspective, the likelihood of once in 100 year events is different, completely separable from that in the 1990s. And this quantifies the changing risk of extreme events. So we can march that forward in time and you see those black dots going on. So we can provide very quantifiable information on changes of extreme events. This is once in a 100-year precipitation events, many other events we can look at under different scenarios. The green dots show different scenarios of the future in which emissions of CO2 may go down and the climate might cool. So we have this wide range of future projections that allow us to provide quantitative estimates of changes in extreme precipitation here, but many other things you can imagine in the climate system that we could look at. So go to my final slide here, please. We want to look forward. So looking ahead, we come from more of the sort of curiosity-driven science side of things, trying to understand the climate system, looking at global scales. So I think there's a tremendous opportunity for much better cooperation with the more applied areas to co-evolve. We don't really, in some sense, understand the applied systems, and we need to learn from that. So I think there's a huge potential for co-design of simulations and kind of model up what we saved to optimize their utility. We're focused on different questions than, say, ASCE may be focused on. So I think there's a huge opportunity for win-win situations. There are likely mismatches between the needed spatial and temporal scales for many of the applications discussed here versus what we can do. We need to bridge that gap somehow. Newer models that are continuously coming online with finer spatial resolution really can help, especially from extreme events. I can't emphasize it enough. Extremes are really critical. For example, recent modeling study we're just publishing now looks at the changes in Santa Ana wind and events in California as we go into the future. Really important phenomenon, just being able to simulate now in global models. Our simulation is really designed for scientific purposes. Is there a better way that could also better serve resilience planning and somehow have a win-win situation and really have this opportunity for a co-design of models and bridge this cultural gap so we can really optimize what we get out of these models in the future? Thanks so much, and I look forward to the discussion.
Great. Thank you, Tom. Let me turn it over to Kelly.
Okay, great. Thank you. Hi, everyone. My name is Kelly Mahoney. I am a research meteorologist also with NOAA. So Tom and I both sit in NOAA's research arm, but in different labs. I'm at the Physical Sciences Lab, which is out in Boulder, Colorado. And so a lot of sort of the culture and makeup of where I sit is similar to where Tom sits, but within the Physical Sciences Lab, we maybe focus a little bit more downchain. We like to say that we do use-inspired research. So yes, it's still curiosity-driven, but we do a lot with partnership engagement and focused research. So I'm just going to give you one example of a project that I've worked on that has been I think a success story, and have been happy to come back to all manner of topics within this spectrum and value chain. So this title slide just speaks to my background is in extreme precipitation. I came to NOAA to work on something called probable maximum precipitation, which I'll introduce in a moment. But I've been kind of embedded within like the dam safety and nuclear infrastructure community. And so I've been kind of coming into the ASCE world a little bit later, more recently over the last few years. If you go to the next slide, just for, again, kind of the sake of kicking off conversation and giving context and one example of where I've been. You don't really need to know a lot about what's on this slide. Some of you may know it all very well, but again, just kind of painting the background that this project that I now lead on a national modernization level is called probable maximum precipitation, and it's been outdated for a long time. The definition is simply the most amount of rainfall that we can expect at a given place over a given period of time. And so that's really central to high hazard infrastructure. So dam safety, nuclear facilities, and so on. Many people across many communities, probably many of you in the room, have been vocal that it's been outdated for decades. And so, spoiler alert, like we now are working on it from a NOAA perspective to modernize this for the nation, but we've been fighting for the opportunity to do that for a while. And so if you go to the final slide, this is just giving an example of one of the steps that we went through in order to get to where we are now, which is an exciting opportunity to do this very applications-based research. And this was at the state level, so probably about 5 or 6 years ago. the states of Colorado and New Mexico were looking to update their extreme precipitation guidance for dam safety. And they had a couple of private sector consultants who knew they were going to approach this from a couple of different ways, but they came to NOAA and said, how can we actually add new science, consider new methods, really represent sort of innovation and the state of the science in this area that we know is outdated. And so we had the opportunity to really start from scratch, but know that we had to get to an end product of guidance for these states. And so in the end, we won this governor's award for partnerships because it required so many partnerships. We did this through a lot of different approaches. We did this, meaning we had success in infusing state level guidance for extreme precipitation for dam safety in a couple of different ways. Some of those were very hands-on, serving up NOAA data sets, similar to like what Tom was talking about, although in our world, they tend to be more forecast driven and reanalysis driven. We said, okay, here's how you can bring these data sets to bear. And then over a lot of work and a lot of time, we got there. I'll also say that there was another component of this project that we didn't know where it would go when we started, but it ended with Colorado being the only state in the nation still to incorporate climate guidance into their dam safety regulations. And so I can talk more about that as we go too. But I think kind of the main point that I wanted to make that distinguished is this kind of work in our research community and at this kind of point in the value chain is that it does require a lot of extra work. And so I think we'll get into this in the questions, but by that, I don't mean to say extra work as in it's inefficient. I think all of the successes that were borne out in this example and many others has been all about offering up menus of opportunities and menus of data sets and methods and approaches and being prepared to fail many times. And that was really central to the success that we eventually found, again, in this state study. It was a long, non-linear path to get to, especially that climate projection information. So I love this kind of work. I'm committed to it, but it's not always the most straight path, but I think it's exciting to have workshops that bring together so many people who obviously have a high threshold and tolerance and commitment to it. So I'll stop there and look forward to the discussion.
Hey, thank you, Kelly. Thank you for reinforcing non-linear, and it's a little messy, right? It has by design. It is a feature, not a bug. All right, let me turn it over to Abby.
Hi, everybody. I'm really happy to be here. So I'm a professor at the University of Colorado, also in Boulder, like Kelly. But I think I put down there, I think my main qualification for speaking here today is in my role as a chair of the ASCE 728 subcommittee on future conditions. So I just have a few slides describing some of the ways in which our process is currently playing out and some things we've been grappling with and what I think some of the implications of those are. So next slide, please. So this co-development really requires a lot of things. One of those is engaging in sustained, committed, and open conversation. So this is a real example. These are almost quotes from a ASCE ballot related to ASCE 7. And you can see that on the same ballot, we had one person saying from an engineering perspective, they didn't find the term non-stationary to be helpful at all. And another person saying that the whole thing should basically be in the title. And so that is a lot of work through that. Next slide, please. We've also spent a lot of time thinking, we put together a committee before we were quite sure what we needed, right? So it was an ideas driven. And so as we thought more about what we needed, we've identified a lot of places where what we need, to Tom's point, isn't exactly what the models were originally developed for. And so we've been really having a lot of productive conversations to work through those issues. So some examples, we're really most interested in rare events and across the spectrum of environmental loading and figuring out how to handle that. Next slide, please. Engineering is inherently local. We design and build at a very specific location. That is a different place from a place that is miles away or even fractions of miles away. And so thinking about how to handle discrepancies in resolution between what the information we have on the climate model side and what we might need for engineering design. Next slide, please. Tom also mentioned uncertainties. Here, I think there's just, how can I put this? I think we all feel that the uncertainties we know about are really important. And then when you put those all together, there's a lot of uncertainties, and figuring out how to operationalize and use those without getting buried under the pile of uncertainties. So I just have one here on the slide that's an example of an uncertainty engineers care about, which is the ratio of snow on the roof to snow on the ground. And the bounds are really wide, right? We don't have a great understanding of that. And so then when you combine that with all these other things, it becomes really important to really work through how we incorporate those sources of uncertainty. Next slide, please. I think that what work we're doing is also providing an opportunity for us as engineers to rethink our assumptions. So, we have historically focused on observations as the basis for our loading. There are great models of the past also that could be improving some of the things we're doing based on our loadings, even without looking towards the future. And as we start to be open to modeling and thinking about models and projections, what can that also improve about other aspects of what we're doing? Next slide. In the ASCE world, ASCE 7, each load is developed differently. Like, they all have the same overarching principles. They're developed differently. When you bring a bunch of people in a room that haven't been at the table in that process, they're kind of like, what the heck? You're telling me you're doing something to get wind loads, and you're doing something like entirely different with a different basis to get snow loads or ice loads, like I have shown here. And I think this is not a call that we need to make everything uniform, but it just provides us, as we try to explain to others what we're doing, knowledgeable others, it helps us think about how could we be improving our existing processes in addition to advancing them. And then finally, last slide, I just think it's really important to think about all this as a foundation for future refinement. Whatever we do is going to have limitations. And so in the co-development process, we really need to be open to saying, that's good enough. And if it's not, where are the areas where it's not good enough, so that we can really tweak that without getting just completely stuck with some of the complexities of the issues that we're dealing with.
All right, thank you, Abby. I was struck by several things that you talked about, this issue of uncertainty, because we got to build something. So how do we manage that? But then the last thing you said about, or slide before last, we tend to look at these individual hazards or perils independently. And often when we are being asked in the A&E sector, hey, I want a resilient bridge. Okay, well, there are multiple stressors that we need to look at, some of which are environmental, some are accidents, man-made threats, those sorts of things. And they're all coming at trying to, they come at them different ways that are important for their discipline. But when you as a practicing engineer and scientist are trying to bring them all together, you understand that the gears don't quite always mesh together. And yet you're trying to give that project owner some confidence. You are building me a bridge that is resilient up to these thresholds, right? And how you characterize those and the uncertainty and all that sort of weaves together. So I'd love to come back to that when we get to discussion. All right, we're up to our last speaker, Eric. Please take it away.
All right, so I'm Eric Zucker from HNTB in New York. I serve as a bridge engineer there, where I design bridges day to day. For those not familiar with HNTB, we're about 7,000 person transportation firm with engineers, professionals, planners, and really focus on the US market. You might be wondering why a bridge engineer is talking about safe bridges at a NOAA workshop, and the answer is right there on the screen. I was deployed as an emergency bridge inspector, that's me with the backpack, during Hurricane Ida in 2021. And as the people walk below rail lines, you can see there where gravel had been just 24 hours before, it really dawned on me the sort of visceral impacts. This is much more than simply upping a safety factor to account for stationarity. This is much more about the real impacts this has, the hidden vulnerabilities on our system, as well as the cascading impacts, such as many New Yorkers not being able to get to work because of this failure of a 12-foot span. And so it really set me on a quest to try to understand how I can better quantify extreme weather data for myself as an engineer. And that led me on quite a journey through NOAA's data sets. So for the next slide, we jump into the multi-radar, multi-sensor data set, which is the one that I landed on as the highest resolution granular data. It's square mile granularity, it's a rainfall accumulation on an hour by hour basis, and it goes back to about 2020. And so I'm able to look back at specific failures that I know about, one of which shown on the right from a bridge in Indiana. And I can look back at what was the rainfall accumulation over a given amount of time that caused that failure. And in this case, it was 10 inches of rain in 6 hours per this data set. And so this ability to better quantify the loads on the structures that we see just really opens up, it's a whole new lens for engineers to look at. We can look at how often these things are happening by doing entire scans of the data set. We can look at the event characteristics, what durations of time they're typically happening on, and how that compares to our design criteria. So there's only one problem after I found this multi-radar, multi-sensor data set, is that it was only located, it was in the cloud, thanks to NOAA's Open Data Dissemination NOAD program, and all the data was there, which is great, but it was stored in 8,670 GIS files per year, one for every single hour of the year. And so while I do have some interns that work for me, I don't have nearly enough interns to download 8,000 files per year and post-process that data. So I went to NOAA with this problem, specifically folks at the NCEI and NCICS, the North Carolina Institute of Climate Studies. We can go to the next slide. This is the solution that was arrived at. Is the data on the left shows the way NOAA provides this. Covers the continental US for rainfall accumulation, and it is slices of time, essentially. And that's great if you have a single moment in time you care about, but if you want to understand the risk faced by a population of structures over a multi-year period, you really need the data structured on the right. And so this is really a collaborative effort with me and NOAA, sort of proof testing codes, swapping back and forth, and allowing us to look into a new way to structure it. And so we ended up with a tabular data structure. So those arrows in point and space, you can see the hour by hour accumulation. So what we've been able to do, for instance, is if I want to get the whole state of New York in the year 2024, every drop of rain that fell per this data set, I'm able to query that from a cloud hosted repository and get that data back in 2 seconds, whole state of New York in 2024. And that allows me to much better understand the near-term extremes that we've been able to see. And so it's opened doors for us to better understand, visualize, and communicate these extremes. Now, the two criticisms that I think this methodology has, number one would be this is only an estimation. This is not ground truth by rain gauges. There is calibration that occurs for MRMS, but it's not. But many of the data sets are simply based on reflectivity and paired to accumulation. To that, I would say that many transportation agencies have limited bandwidth to be able to look at extremes as they're occurring and have recently occurred. Some of them only get National Weather Service blurbs that they get, and that's their primary source. Others use rain gauges, which are 30 miles in center, and still others use things like Weather Underground house rain gauges as their best intelligence. And so this data set, while not perfect, while an estimation, is orders of magnitude more granular and high resolution than some of the current methodologies being used by transportation agencies. The other criticism I get on these methodologies is simply that there's only 4 or 5 years worth of data. We, of course, cannot project 75 years out based on 4 years worth of data. I'm not suggesting that, but I still believe for the engineering community of practice, this 4 or 5 years worth of data set that we have is deeply valuable for a couple of different reasons. One is it can improve situational awareness during the event and immediately after the event to allow more effective response and inspection of potentially damaged structures. We can quantify, visualize, and demonstrate those extremes to stakeholders and also to justify funding. We can look at improving our forensics by looking at loads that have occurred at a much more granular level than rain gauges would allow. We can even look at a fragility assessment, the risk of population of assets, and what loads have caused which failures to update what types of structures have seen failures and those fragility curves. And finally, we can vet new resilient strategies in looking at the way we design bridges by making them either safe to fail, look at rapid replaceability, or simply knowing certain areas will be overtopped and trying to understand what those overtopping water loads can mean for bridge design. Thank you.
Thank you, Eric. There's so much in there I want to pounce on. So much, and it'll come into, I think, in our second question that I'll pose to the group is around this issue of what do you do when you don't have things that are fit to purpose? Because we've got to move forward. Our clients need to move forward. What do you do? But I'm going to postpone that and maybe come back. And I really like how you finished with this example of working closely with NCEI and the state, right, to try to make what's being provided better and easier for you to ingest and use. And so I think the first question that I want to take and everyone on the panel have an opportunity to respond is, what does co-development really look like? And we could probably have lots of good examples, lots of bad examples, and fill in the rest of the time. But I'd like to ask each panelist as we go through, and I might maybe go with, I'm going to go right to left on my screen. So I might start with Kelly so that Eric can catch his breath. What are maybe your best example of what co-development looks like when it's worked well? What was it about it that made it work well, that messy process? And what's one thing that is a persistent challenge that maybe might inspire some folks here within this task force to try to tackle? So we'll start first with Kelly.
Okay, so at the risk of saying something obvious, but we'll consider it our starting place. So when things are going well, I would say that you note and could clearly articulate iterative progress. And I mean that because it's so easy between scientists and engineers equally to get lost in the weeds forever and really lose track of progress. So I would say that as my career anyway has gone on, the value of having like a third party in the room to check people on that iterative progress has been really useful. And it kind of provides its own momentum and positive energy to that co-development process and keeps it moving forward, because everything that you do in co-development is hard and is going to look messy for a while. So having somebody to kind of zoom out and keep it moving at least iteratively forward is a good indicator. Indicators is going poorly. This is kind of the inverse of that, but I would just say consecutive meetings of talking past each other, and in kind of like disengaged language. Like I've been in projects where the scientists come with their tools and their data sets, and the users are like, oh, that's really interesting. And we're like, great, they think it's interesting. That's fantastic. So I guess they know how they're going to use it. And it took me a really, really long time, and I'm still not really good at it, to say like, it's interesting, like you think you'll use it. How do you think you'll use it? Because I think there's also this assumption that everybody always knows more than you in like the most general of ways. But I think especially in like multidisciplinary work, you're kind of like, oh, the user knows what they're going to do with this, and they think the scientist knows what they're going to tell me to do with it. So yeah, I think multiple gatherings or a certain amount of time that goes on without anyone actually offering up or having the courage to ask, is this landing like in a productive way? So yeah, those are two basic things that come to mind when I kind of reflect back on projects like this.
Thank you, Kelly. It's hitting we don't want to make things that are useful. We want things that are used, and really trying to understand enough and having the confidence, or at least absence of fear, to ask what might feel like a really uncomfortable question of, this isn't really something that we need, or it isn't provided in a way that we see immediately. This is how we're going to use it, and being able to have enough of a relationship to say that and not upset folks. Maybe Abby, maybe we'll turn to you next to answer this.
Yeah, so I like we're in the midst of what we're doing. I will say that in general, I've been very inspired by what's gone on at the ASD 7 Future Conditions Subcommittee. And I think like I've actually had a lot of joy in learning new things and figuring out how different pieces of the puzzle are going to work together. And so I think bringing that to the table and a sense of curiosity has been really important to figure out how we can do this work and do it in a way that doesn't turn everything into a many $million research project, which we don't have for many reasons, right? On the other hand, where we've struggled, I think we all have our silos, we have our egos, we have our traditions in our discipline, and sometimes those are not helpful, right? Like we may have always done something some way, and now that we have a new challenge, or and new people at the table, doing it that way just may not work anymore. And so where I've seen us struggle is where we get stuck, where some people are not letting go of some of that baggage, or really reflecting on which of those things really need to be brought to this particular effort, and which things can be set aside in the interest of co-development.
Thank you, Abby. Tom.
Yeah, this is a great question. I come at it from the sort of global modeling side. So what's crucial, at least from the community I'm in, is just to better understand the questions that are being asked and the precise problems to try and address, and then to see if can we or can we not make useful contributions with some of our modeling data to the questions in mind. For example, Eric's very nice presentation looking at very fine scale precipitation observations and looking at risks. And I think those are the kind of things that some of our models would be able to contribute to. For example, I mentioned a model we call SHIELD, which is very fine resolution, fine resolution for a global model is 3 kilometers. Maybe that's not fine resolution for some people, but for us it is. And so you can imagine a model like that, which has really been trained in a weather prediction model, an excellent weather prediction model, but also can be used in projecting climate change and the risks of these extremes. Could be a very useful tool, whereas our very coarse resolution models might not be. So for us, people and the climate modeling side are keenly interested in having these models used for many of these challenges. But the crucial thing is to really understand what that question is and what tools should be used. And that's really appropriate. You know, medical science, do you need an MRI? Do you need an X-ray? What do you need? And for here, it's really understanding what the precise question is, and then can we, or sometimes the answer is no, that the models simply are not useful for the questions in mind, but sometimes they are. So that's really the key issue for us is understanding what the precise question is being asked in terms of user needs, application needs, and then we can work and see, is there something we can do, or sometimes the answer is no. But that's, to me, the essential is understanding that precise question.
Yeah, that also, though, requires people to know what question, how to frame the question. What is the question I'm asking? And that's where, and I'm going to turn it over to Eric too to speak. As I have moved from being in the government and production and policy side to sitting down with owners, right? Part of my job is helping them know what questions to ask, to really be able to articulate, not vague, hi, I'm working with DC water utility and we need resilience in our water supply. We need a second source. Okay, well, what does that mean? How many hours? How much water for how long? We need to get specific. And so there is a bit of an iterative process, right? To even be able to get to that point where they can characterize that purpose for which they need, you know, supporting science and information. But let me stop. Let me turn it to Eric for your opportunity to weigh in on this. You've already given us a really good example that we have up still on screen. What else, what works, and where do you still see challenges?
Yeah, so I would say that the collaboration piece between disciplines is so key, which is sort of a cliche at this point, but you know, I feel very fortunate to have worked so closely with NOAA up to this point. A lot of credit goes to Ellen McRae, who I believe is on the call today. We had a chance encounter at the TRB session, and she said, "Oh, we'll follow up." And most people say that and they never follow up. But Ellen got me on a call with the team from NOD, and we went from there. In working with the team at NCEI and then through the industry proving ground at NOAA as well, I was able to articulate what I needed and show them how I could do it. There was lots of sort of code snippets sent back and forth to figure out the best way forward and reduce the complexity and efficiency by orders of magnitude. Otherwise, it wouldn't have been feasible. But there was a lot of stepping back and, you know, giving the 101 explanation of, well, here's why it's important for bridges, or here's the basic tenets of meteorology that I had to learn a whole lot. And I think really trying to meet in the middle with our expertise and our domain knowledge was really the biggest part. But we had an end goal, which is we want to make this data as usable as possible to as many people as possible. So that was really the North Star we had as we push this forward.
What would be an example, though, of where you still see difficulty, right? Where we probably have a little ways to go.
Yeah. Well, I think the one thing that engineers and scientists both have in common is that neither one likes to move forward without a perfect data set. And of course, we know that every data set has challenges and limitations. So I think articulating the way that data sets are used on both fronts, right, to the engineers and to the scientists, understanding the limitations, which oftentimes are not sort of communicated in a similar language and methodologies, that really is the place where the most conversation is needed to go forward, especially among practitioners and engineers who really don't have this mental bandwidth to stop for a day and think about these problems. They're working on the challenge right in front of them. They want quick answers, and unfortunately, many of these things are much more complex to boil down to a single number or return period event when we're looking at the multifaceted aspect of risk of how structures fail.
Well, you gave me a wonderful segue too into sort of the next question, this issue of what you do when the data are not yet fit to purpose, right? And I'm speaking, and again, there are probably some of you in the room. I don't know if Vich is, I don't think he's still on the line. He was one of a number of federal agency folks that I leaned on pretty hard when we were working on the federal flood standard and what is best available actionable climate science. And this tension between, and I guess I was cursed enough to know at the end of the day, someone in the community is going to build this townhouse complex to an elevation. They can't look at, you know, error bands. They've got to build it to a number, and the community needs to permit it, and someone's going to insure it. There are all of these things that require an answer, and yet we understand on the science generating side that we have uncertainty. We have, you know, this really complex landscape that we've got to try to work within. And so I probably annoyed some of my science colleagues equally with some of these challenges. So I might ask you all, and then after this, I think we'll maybe do a check in the room for questions. But what have you seen as effective strategies to manage the fact that we don't yet have, we have people who need to act, we have owners who want to build projects and operate in the world, and yet we don't have all of the data that we wish we had. Some are working on it, but we don't yet have it. How do you manage that in terms of keeping some sense of scientific integrity, characterizing, communicating uncertainty? What are, and maybe those are some of the examples, but maybe we'll go through and see what you have seen, about where we can strike that balance, that you're not, you know, forestalling any action, but you're trying to move forward in a way that you've sort of hedged bets and really been transparent with respect to the information that you do and do not have. Maybe who would like to take that first? Maybe instead of calling on folks, let's see who wants to jump in.
I can jump in. One thing that we found helpful is trying to work on it, like the question that Tom brought up. You need a good question, but kind of working at it from both sides. So like on the one side, here's what the climate science is telling us about future projections of extreme loads. On the other side, here's what we can do in a building standard, which is, you know, like we're not going to increase a load by 2% most likely. So you know, it's probably going to be nice round numbers, 5, 10%, and 20%. And so sometimes there's some value in saying like, is 5, 10, or 20% increase the right number? As opposed to saying what is like where does that meet up with what the climate model is? So like coming at it from both directions, recognizing what your answer is going to look like, not to like drive the solution, but to figure out if you really only have a menu of options for what you're going to do, then that might guide how you pull from the climate data to figure out which of those menu of options is acceptable or appropriate.
Oh, that's great. Tom?
Yeah, maybe I can just jump in. So we're obviously everyone is always dealing with uncertainty, but one of the huge uncertainties for us in sort of the modeling field is how the atmospheric composition will look like 20 years from now, 40 years from now, 60 years from now. And so one of the ways that we certainly trying to at least address this or get a handle on this is we'll use our models with many, many different assumptions about future activity, future greenhouse gas concentrations, aerosol concentrations, et cetera. So to develop these very large sets of simulations across very different scenarios of future forcing to get as a good a handle as we can, given imperfect data, on the likely distributional changes in various things. And we don't know what the future is going to hold in terms of a lot of the drivers in the climate system. But if we do as many cases as we can probing this big parameter space of future emission scenarios, it at least gives us a handle on estimating uncertainty and sometimes where the surprises are, what we don't know about. So I think really looking at a wide range of possible future states in a way that we can quantify, you know, within the model world very well, the likelihood of certain changes. That's one of the important factors, at least for us, in dealing with uncertainty.
I'll only say from
Go ahead, Eric.
I'll only say from my perspective on the uncertainty and the limitation side, you know, people sort of lump a lot of times practitioners in one bucket, and there's such a wide variety of both space and time that they consider. Some people just want to know, like, when's the roadway going to overtop so I can send some people there to go look at it. Other people are looking at, you know, I have my eyes on this one specific structure, one specific place on the river. I want to know what's going to happen here based on the best available data, whereas others really are more holistic over an entire population of assets and trying to understand. So while they all have very different perspectives, I always try to tailor the uncertainty conversations about time, about space, about intensity to where they're at, because oftentimes they can't agree or find a common language even amongst those three perspectives. So it really depends on who you're talking to on the practitioner side is what I found.
Kelly?
Yeah, I was just gonna say, I mean, I think on this general topic, there's been so much, so much in the literature and things about the concept of like satisficing over optimizing. And just one example of that also, and so we talked about like having menus of options, and that can be good and bad. Is like turning the question of like, okay, you have this menu. Now, and so we were asked at one point, like, well, our tolerance for this kind of information is at this level. Where are you most confident? Like, what's like the physical signal, the qualitative signal where you're most confident? And for extreme precipitation in this example, it was kind of in just like the simple Clausius-Clapeyron 7% per degree relationship. And I think Ken dropped off, but Ken Kunkel was critical to this conversation. And in the end, despite having crunched through lots of higher end quantitative approaches, the user just wanted where scientists were most confident in the signal. And so we went with that instead. And so I shouldn't say instead, we went with that because that was the best fit. And it wasn't perfect, but it was the best fit.
Oh, interesting. Thank you, Kelly. It looks like Willie has a question. I haven't seen anything in the Q&A, but maybe we'll take this question from Willie, and then either Dan or whoever's sort of managing the conversation in the room will open it up to see if there's some questions there. So Willie?
Okay, thank you, Maria. Thank you, panel. Great discussion. And this issue of uncertainty is something that as scientists we've lived with forever, and we will live with forever. There's always limitations, there's always conditions. But one of the things I found that really helps is having a conversation with the user of the information you're trying to provide to understand what, where do they come from? Are they a scientist? Are they not a scientist? Are they a financial person? Or what, do they know anything about climate science? And how fluent are they in sort of analyzing data, and understanding that concept? But I think that running sensitivity analysis around thresholds that they give you that are material to them is very helpful. Thus, you can put error bars on it and tell them, listen, we're somewhere in between, somewhere in this error bar, the mean is this, and and also relate to them how much skill there is in the data. Okay, so if they're asking for wind information, that's way different than asking for heat or precipitation. So that's the approach that I've taken. It's a slog, okay? It's not easy, especially when you're talking to people that are not technical, for them to understand that. But they do, in their own way, they do sensitivity analysis on all sorts of things. So they're familiar with the concept. So thank you.
Thank you, Willie. All right, looks like Dan's at the podium. Dan, are there questions in the room?
I'm at the podium right now. We'll take questions in the room if anybody has one.
If not, I have another question in my hip pocket for the
Go ahead. We're digesting.
Food coma. I told you all to come with caffeine. Okay. One of the questions that I wanted to try to come back to was this, and I think part of the impetus here for the workshop and everything is, what can ASCE do? Or yes, ASCE, but I think more broadly about intermediaries and facilitating organizations. I'd love to hear from the panel what forums, what intermediaries, Tom's wonderful, but he's only got so much bandwidth, and if he has too many people trying to come at him asking for information, how can you synthesize that down and he and people like him develop priorities for where they're going to expend their FY26 budget and resources. So and vice versa, right? Eric and others among us in the A&E community, part of our value to our organization is having awareness of data sets and innovations and things that are going on, but we all have limited bandwidth. And so I think there is an important role for organizations, and I'll just use the catch-all of sort of intermediaries, to try to facilitate. NOAA, in many cases, having come from the part of NOAA that liked to sit in that role of being a connector and translator, well, there's one. But who else, or what other forums, so, specific convenings, or people, groups who have as part of their day job a connecting and facilitating role, which ones have felt like the most effective? And are there more things that intermediaries like ASCE can do? So maybe, who would like to maybe take that first? I'm going to give this is another chance to give shout outs to people like Ellen and
I was just going to say, can we just answer it with one word, and that's Ellen? Like, that's the intermediary, yeah. And where Ellen sat within NOAA, she was accumulating a community of people, but those, as Ellen can attest, those communities and support for that work, let's just say it ebbs and flows. And I'll end with a positive here in that, and Ellen was key in doing this, when there are opportunities for big projects and big investments, for example, the IIJA, bipartisan infrastructure law stuff, carving out a very real, substantial, continuous area of support for those identified intermediaries is key to the success. And it does not usually happen for smaller scale projects. So I think that's the citation of a good example and an area of opportunity. And I think, yeah, so that's an opportunity where ASCE and similar can look to fill.
Hey, Maria?
Eric? Yep.
Are you going down through the panel with the same question, or do you have an opportunity for a new question?
Hey, if it comes up, and then again, if we have a lull just until our time expires,
Okay,
we can
go for it.
Back to that.
Carry forth.
Okay, well,
So
no, did it sound like you had somebody in the room that had a question, or no?
I had a question, but I can wait.
Okay. Abby, why don't you go ahead, and then we'll go back to that.
I was just going to say that, and this is not a near-term solution to this problem, where everyone in this room is madly acting as intermediaries and to the extent of their capacity, right? But where I sit as an educator, I think that we really have an opportunity to bring these things together, incorporating more of these examples and climate science into our curriculum and engineering. And there might be other ways in other aspects I'm less familiar with. And I think ASCE has historically and continue to be really helpful in helping us, because I don't think the students that we're currently seeing now are going to be as separated on some of these issues as we have been. And so I think we really want to think too about how can we set them up for success in addition to working forward with the workforce we currently have.
I think that's a really important point. There are just a number of places where how we are training the experts and the practitioners of the future has to evolve. And this idea of making it just, I came into NOAA, it was like, what do you mean we're going to be driven by what our users are saying we do? That's not how I was trained. I was trained to do curiosity-driven science. Oh, I need to change. And so having that just within the DNA of our, up and coming practitioners, and even if they don't go into the field, they're going to be existing in communities where we're making infrastructure and planning decisions every day, right? So how can they help, in that be better equipped? Dan?
Thanks. I actually have a question for Abby, and I apologize. I've been kind of doing double duty here, getting ready for the last session. But can you just remind me and the audience, like the timeline for balloting for ASCE 7, and really more than that, when do we anticipate some of these underlying data sets being made available? Can you kind of close that loop for me a little bit, or is that too much to ask?
Well, I'll try to answer it. The answer might not be to your satisfaction. So we are working on ASCE 728, which needs to be done by early 2027, and the balloting process is long. It's, a consensus-based, rigorous process where we need to respond to all of the comments. And so we will be providing to the main committee a complete ballot with draft numbers, or maybe in some cases final numbers, early this fall, but then there will still be a process of review. Now, in developing, as those of you know, like in getting something that can be written down into a standard, we've had to set some things aside and say we're going to deal with that later. There's probably some more things we're going to have to set aside, but we do anticipate having some draft numbers soon. And when exactly that will all be available, I'm not sure, but we're certainly, all of that, the material will be incorporated into the hazard tool. So the things that are referenced, or the data set, the values that are used in the ASCE 7 standard will be kind of seamlessly integrated with ASCE's existing infrastructure to kind of close that loop for engineers.
All right, thanks, Abby. I appreciate that. Maria, I'm going to turn it back over to you.
I guess my question is, and I wanted to make sure Eric had come off of mute, and so I wanted to give him a chance if he had, and then I think we're about at time, right?
Yep. No,
Yeah, and I think the original question was, how can we make NOAA and other intermediaries better interact with different agencies? And I was always very cognizant when I had, conversations with Dr. Kunkel or Russ Bose or others at NCEI. They're single people, right? And they have numerous sectors to cover. So I was very grateful for that time, but also felt some level of responsibility to then pass it on to other areas of the transportation space, right, where I sit. And I think organizations like AASHTO, which is essentially a collection of all state DOTs, is one way to do that. There's other similar agencies for the transit space, like public transit. And so I think that's those types of organizations sort of being the intermediary between them. I know there was an MOU between NOAA and US DOT, I believe, as well. Could be another vehicle to do that, I guess, pun intended with vehicle.
Well, I think there are a number of, now that I have firmly entrenched back in the engineering space, and working across resilience is not its own market. It is something that underpins everything we do. And so I am working with SAME, the military engineers. I am working with, APTA and American Waterworks and just all of these different groups. And so to the extent that, those of you who are practicing engineers have your professional associations, ASCE is a wonderful umbrella, but are there some of these other professional societies and things where we can roll up our sleeves a little bit more? Maybe that's already happening and I just don't have visibility on it, so I apologize if I'm speaking out of turn. But I think in particular SAME and some of the things that they're doing with bases and in supporting border communities and that sort of thing, I think there's just a lot of opportunity to really get that message about these are the needs, these are the questions we're struggling to answer. What do you got? What can we produce together? There are just, I think, many opportunities there. All right, so thanks, Dan. I'm going to shut up now. Thank you, panelists. We really appreciate everyone tuning in. And back to you, Dan.
All right, well, thank you. Let's have a hand for this panel. I guess I'm going to do a little editorializing here. I think some of this work here is so essential to civil engineering design and our standards process, and yet some of this work, it may be some of the most vulnerable work in the federal space because of administration decisions about climate change and how they want to handle climate change. I know we don't really like to talk about that because we're all polite, but we have to keep that in mind. If ASCE and the civil engineering community wants these products to be available, we have to make sure that we articulate that need. And I think we're kind of setting up some of the discussion here for the remainder of the meeting.